So, then I welcome you to the last actual lecture in parallel and distributed computing in this summer term 2025. There will be one more meeting of us where we discuss an old exam. So this will happen next week, and then we also have to discuss your homework, for which we still need to get some appointments with you, but there will be no further lecture on the 18th because then I was already... Okay, I will not be on the plane at this time, but I have to be on the airport at this time. Yeah, so there is no way that I can give a lecture in 2 weeks. We are in principle done with the content, and today there is supposed to be more like like a compute session only, which is a little bit disadvantageous now because first of the attendance, and the other thing is the CUDA queues are all occupied, so we may not be able to do actually the computations, but we should be able to do some implementation. Yeah, so this is already getting us close to what we do in the exam, because in the exam you cannot test your program, yeah, because you have to do it on hand. So now it's a little bit old-fashioned style. You have to get it right the first time, if you will, because that's a bit the reality of this batch systems. Yeah, so if they are not free, you have to wait, and the reality of high performance computing is you're not doing high performance computing because you have very simple stuff to solve. So one reality is that's difficult for science is this very, very long feedback loop, because we do simulations that take months, yeah, not weeks, months, on high performance computers. So, I mean, with 20 or 200, I think the 200 billion degrees of freedom is not unusual, yeah. And you see, Phoenix is already 10 years old. Okay, so what you do in your homework is supposed not to take longer than a few seconds, yeah. So you're not supposed to occupy the GPU stuff for more than a few seconds, because we are just guests on this, right? Okay, so there is again this matrix. There is again something in the folder for lecture 11, and this is called matrix multiply. Yeah, I suggest now while I'm talking, you do the start up of your computer, but still listen to me. Yeah, but since the computers are so slow, get them already started up. Okay, so that's what we are going to use, and I skipped over the title of today. So the title that we are talking about is wrappers. So what is a wrapper? A wrapper is kind of an interface where you put around some functionality to make it available in different contexts. Yeah, and this nowadays, if you think about parallelization, then you kind of may have the trouble or the advantage, whatever you think about this. So you have different ways. So we learned about different ways to parallelize your code, and often, very often, this depends on the hardware that is accessible to you, how you would do this. Yeah, and the trouble with this is, of course, that you would have to implement your code, your functionality, for all these different ways of doing it. Yeah, for running it on the CPU, for running it on the CPU with vectorization, for doing with somehow with MPI, with OpenMP, with threads. Yeah, so you always you have to start kind of from scratch. Yeah, and a wrapper is now something that takes your functionality in a way that does not depend on the hardware you are going to implement it on, and so puts it into this wrapping like a present, and then all you need to do is for the different approaches that you want to use is to write an interface, yeah, that does the startup. Okay, so this is the surrounding. So this is not what is on the slide here. What is on the slide here is some functionality that we need in order to do something on some functionality that we need for doing wrappers when we use them together with the GPU and in particular with CUDA. Yeah, so in CUDA we learned that we can write a device function, and the device function will be compilated obviously for the device, and the device being the graphics card. Yeah, so if you write, this means if you define a device function, then this device function will only run on your device because it's only compiled on the device. Now, CUDA allows you to also indicate that you want to have this function compilated for the same function compilated for the host being the CPU, by indicating here where you have this keyword device, you can also add a keyword host. Yeah, so you can define a host device function. So I mean, if you don't write device here, then it will assume that it is a host function. You can also write host function, but this is kind of redundant. Yeah, so everything else will be executed on. So if you don't say that that is a function for the device, then it's the function for the host. But if it's already a function for the device, you can indicate that it's also a function for the host, which means that it will be compiled twice. It will be compiled so the same code, yeah, the same code will be compiled for the device and for the host. Right. So this, so please always distinguish the difference between a device function and a global function. Or can you give me an explanation what is the difference between device and global function in CUDA? Clear or not? If you don't get an answer as a professor, you always have to think. So either it's too clear or it's not clear at all. So what is the global function good for?
running on the device.
Yes, so the global function is the thing that will run in, okay, that you usually call with your blocks and your threads. Yeah, so this will now run in parallel. This function here, the global function, can now call. So the device function is always called by the device. Yeah. So what you can now very simply do here. So this is the simplest kind of wrapping around this function, if you will. Yeah. The device function. The global function has its block IDs and its index IDs. And now let's taking the thread IDs, I mean, yeah. So now, for example, we can just use the thread ID here, yeah, to call here the host device function. And this will be executed, of course, on the device. So now this is this global void. Yeah, we call this with. Let me remember this. This is one block with 256 threads each. I hope I'm saying this correct, because I'm not. This is the trouble. If you're a professor, you always have to teach stuff that you're not doing all day long. Yeah, so I make mistakes here. Don't mind. Yeah. So this is one block and 256 threads. We call this by n x. Then so this is CUDA device synchronized. Wait for the GPU to finish before accessing on the host. Okay. All right. So this is, I think we have not talked about this, right? No. Okay. Yeah. Yes, we did not talk about this, and this may cause some problems, because the thing with GPUs, of course, is that they are supposed to do graphic display stuff. Yeah. So when you call a function on the GPU, this will usually return right away, because the idea is you're sending something off the screen and you're not waiting for the screen to do anything. Yeah? So these functions are not blocking. And at least this is what I believe. So we can look this up later again. Yeah. So if they are not blocking, you may get into the trouble that you start freeing it before the job is done. Yeah. This is why you should call this CUDA device synchronized. So as I said, I'm not the guy who is programming on CUDA every day. Yeah, so we have to learn these things together. Okay. Now let's talk about these wrappers. Okay, so one thing that I have to say up front is that wrappers come with a cost. They are not for free. Yeah. So wrappers, because wrappers always have to call functions, and depending on your circumstances, function calls can be extremely expensive. Extremely expensive, sometimes. Yeah, unbelievable expensive. I have seen this. So, so you always, when you use wrappers, you should check whether this slows down your code significantly compared to when you don't use wrappers. But the good thing with wrappers is that you can use one code on different machines. Okay, So what does a wrapper do? This wrapper, so in this host device functions that we want to wrap, we have all the functionality implemented that we want to do, that we wanted to do, but we do this independently of the hardware. So we do not implement something that is specific to how we want to execute it. Yeah, only the functionality, and the hardware specifics now come into the wrapper. So the hardware specifics on a GPU and using CUDA is that there are these quantities, block ID X, block ID block index Y, and so on, yeah, and this dimension. So this is something that is CUDA specific. That is something that you get from CUDA. And so usually in another context you would loop over things, but here you get these things there, and now you get your coordinates that come out of these, thread indices, and you hand them together with your other arguments to the device function, yeah, that you wanted to wrap. Okay, actually that's more or less all about this. So now, since you have this functionality isolated, you can either use this wrapper in CUDA to call your functionality, or you could also call this, because it's a host device function, you can call it from the host, but then you have to identify your, Then you somehow have to identify these indices that you need. And in the usual way, if you go over, for example, a three-dimensional field, yeah, so what you would do is you would wrap this into three loops, right? So this is now what you would do. You have the same function here, but as a wrapper around all of this, you have all of these loops. Right. So more or less the last thing to think about is what data, would you use if this is done on a GPU. In particular, if you use a managed data device. So managed memory, yeah, not device, yeah. So you need to know that when you call the same function from the host, using also the same, in this case, using the same pointer. And I remind you, if you use CUDA malloc managed, then we use one pointer for memory on the host and memory on the device. Yeah, we access both of them with the same pointer. However, they are different memories. So if the function is called from the host, it will assume that your pointer points to the host memory, while when it is called from the device, it will assume that it's called from the device memory. Oh. So the pointer points to the, please.
You must do that for every pointer? Because else it will be...
So you must, what you mean you must? I mean, this is something that happens. This is not something that must. So what you mean with must?
Oh, I thought this function returns the actual pointer.
No, it's not.
But like internally, though.
Okay, this is not. No, what I mean by this, we are using a pointer. We always have to access our data through a pointer because we allocated this. Yeah. So either you allocate memory on the device and on the host, and then you have two pointers. And when you do this, you need to take the correct pointer. As I said last time, you have an address, but if your address makes sense only together with the country you are in, right? I mean, suppose that two countries. So there used to be in East Germany or West Germany. Maybe that's not so amazing. But for example, in India and Pakistan, you may know that there is the same cities in both places because they had to move. Also, that there may be different places with the same address in different countries, right? So you have to go to the right place. So you need to care about this, because if you don't care about this, this will go wrong. So if you have non-managed data, of course you have to use the correct pointer, the pointer in this correct. Say if you call it from the host, then you have to get the pointer in the host. Yeah. If you are in the device, you have to get the pointer in the device. If you used managed data, then you have only one pointer in both places. So this will be interpreted in a different way depending on from where you call this, and this will lead to so-called memory trashing. This is something that you want to avoid. So, what is memory trashing? So suppose you are lazy and use this managed data, yeah, so that you can call the same so that the copies are the two copies that physically exist, yeah, are synchronized by CUDA itself, yeah. So this means whenever you change one in one place, it becomes inconsistent in the other place, yeah. So it will be marked as dirty. So that when you try to access in the other place, it knows it is dirty and I have to make the copy. So this means and it usually does the copy of the entire thing. Yeah? So if you are not careful and you are working on the same data from the CPU and from the GPU at the same time, or you do one operation here, then the other here, then again and again, then every time your memory becomes dirty and the version that you have goes into the trash and has to be recopied from the other side. Yeah? So if you are not careful with accessing managed data, what you're going to do is you're causing a lot of memory traffic, which will slow down your computation in a way that will usually make it much slower than what would happen otherwise. I mean, other than when you just did it on the computation on the CPU, for example. Okay, so now this comes to as I said, I don't have a lot to say today, so we'll try to do a little bit more an exercise part. There will be, or there is in this folder is a matrix multiply dot CUDA, where this is basically an implementation similar to what you did last week. So I was not implementing it, so I had to take it from last year this time. And the idea, what we are going to do now, is to write wrappers for the functionality such that we can call the same thing from CUDA and the CPU. Yeah? And then what we want to do is to split up our problem. We want to split up our problem and I noticed this may be necessary to change this. Yeah, so this is not in the job file. I currently put it to 1. Yeah, because you have to take it. Okay, we'll discuss. So yes, getting back to the task. The idea of the task is that we split up our problem, do part of the computation on the GPU and do another part on the computation on the CPU. But on the CPU, we want to use several tasks. Yeah, so we want to multi-thread on the CPU by using multiple threads and then also using the GPU. And there, this is where we have this picture for. You should be aware that threads in the CPU and in the GPU work very, very differently. So I briefly talked about this context switching between threads on the CPU. Do you remember? So what happens if a thread on the CPU switches its context? Oh, okay. Maybe this question was not correctly formulated. So if you go from one, so the thread does not change the context. The machine changes its context by going from one thread to another thread, right? By switching between threads. Yeah? So what will the CPU do when it goes from one thread to another thread? I mean, I come from the time when there was one core in a CPU, but we had multi-threading 30 years ago, yeah? 40 years ago, maybe 2. So there are many, many threads on only one core. And they are always switching between the threads, so that you as a user have the impression that several things work at the same time. Now, we proceeded to a time where actually things are working in parallel on your computer. But like the laptop here may have only 4 or 8, parallel units. So it can only physically process 8 threads at a time. The GPU can process much more threads at a time, but also not, of the order of a few thousands at the same time. Yeah, but not all of them at the same time. So the GPU has something that's called fast context switching. Fast context switching means that when the processor goes from one thread to another thread, it simply switches its registers. Yeah? So it has, because the GPU has a lot of registers, and the executable unit can just switch to other registers and go on calculating. Yeah? So this means the GPU can instantaneously forget what it was doing and do something else. Yeah? So it goes from one task it's doing to another task that is doing, and it just switches its memory. On the CPU, there are fewer registers. So when you have a context switch, what you are classically doing is you have to take your working memory, which are your registers, and put them on the stack. So you have to copy them away. Then you have to load from another stack the working memory of the other task, and then you can go on working. So this copying, this is the overhead of the context switch. Yeah? And this makes it expensive to have many, many threads. So why is this important? This is important because you have a completely different way of implementing code in multi-threading when you do it on the CPU or on the GPU. You see, if we may go back here, is what you basically do is for every entry in your matrix, yeah, you will call its own thread. So this is the efficient way of doing it on the GPU. So basically, think about you have your finite element system somewhere where you have a million elements, so you will naturally call a million threads. Yeah? So each element will be processed by one thread. If you do this with multi-threading on the CPU, then you will generate a lot of threads that have to change their context, going from one to another, and so you spend all your time changing the context. So you're not going to do it this way. Instead, you want each thread to do as much work as possible, because changing the context is expensive, right? So you will have a loop for each thread. Here, you have this is like you have 6 threads here, and now you have very thin threads here. So here, the threads will, so if you have, so the difference basically is, so you want to split this up as little as necessary. Say you have 20 cores in your computer as the nodes on Phoenix have, then you don't want to have more than 20 threads. When you take more than 20 threads, it will be getting more expensive. However, if you have a GPU with 6,000 cores, yeah, then you will still use a million threads because you have fast context switching. Here it's more efficient to actually call all of them by their own threads. Okay, so I'm talking slowly, I know. Now we come to the actual challenge that we want to do. So we very simply want to do the A times B matrix going to a C matrix, yeah, and this we want to split up into a larger part that we do on the CPU and a smaller part that we do on the larger part that we do on the GPU and a smaller part that we do on the CPU, but also on the CPU with multiple threads. So we'll split up this matrix, and it is important, we'll put only a part of the A matrix on the GPU, and we also calculate only a part of the C matrix on the GPU, such that we such that we do not need to trash the C matrix when both of them work on the same thing at the same time, right? So we do just this computation here, and when both of them are done, we put both of them together. Do I have anything else? No, actually, that's already it. Yeah, maybe. So it's depend on how far we get with this. So, okay, let me see. So in lecture 11, I've put the n tasks per node. So if we want to have more threads, then we have to put this higher, like we have. So this gives us the possibility to have more threads on at the same time. Yeah, now the challenge now is that you are supposed to do this, and one thing I encourage you now. Okay, so there's because I saw you in the past working kind of in parallel. Now I suggest that we do this more sequentially, in the sense that in order for you to work together, we also do some peer programming style. You know peer programming, pair programming. So there are two, now there's something that's called co-pilots. That's unfortunately artificial intelligence. So usually, before there was co-pilot, there was human co-pilots. Somebody is programming and the other one is sitting next to it and tells them what to do. And then after 10 minutes you switch and the other one is programming it. So I suggest we are going to try this out this way. I'm stopping the recording now.